Eddy current break. We have to explain what is eddy current break. An eddy current break. An eddy current break under bracket also known as an induction break, also known as an induction break, comma, electric break or electric retarder. An eddy current break, that is induction break or electric retarder, is a device used to slow or stop a moving object. It consists of a conductive piece of metal. It consists of a conductive piece of metal, either a straight bar or a disc or a circular disc, comma, which moves through a magnetic field. It consists of a conducting piece of metal, either a straight bar or a disc, which moves through a magnetic field of permanent magnet or through a magnetic field of permanent magnet or an electromagnet when it moves past the magnetic field of a stationary magnet, comma, the magnet exerts a drag force on the metal bar or metallic disc, which opposes its motion due to flow of circular electric currents called eddy currents. Induced in the metal bar or metallic disc, induced in the metal by the magnetic field. When it moves past the magnetic field of a stationary magnet, the magnet exerts a drag force. In this case, the conductive sheet of metal is not made of ferromagnetic substance. The conducting sheet of metal is not made of ferromagnetic metal such as iron or steel. Conducting sheet of metal is not made of ferromagnetic metal such as iron or steel. Usually copper or aluminium, which are paramagnetic substance, copper or aluminium are used. Which are not attracted to a magnet. Usually copper or aluminium are used which are not attracted to a magnet. The brake does not work by the simple attraction of a ferromagnetic metal to the magnet. So in this diagram we have a circular disc of metal and current is sent to the metallic disc. In the diagram, this is a circular metal disc. This is a circular metal disc which is capable to rotate about its own axis. This is a circular disc of metal made of copper. This is a circular disc or circular metallic disc or circular metal plate which is capable to rotate about its own axis. Circular metal plate, and it is made of copper usually. In the diagram, these are the two poles. These are the two poles of a magnet which can apply magnetic field to the circular metal plate. When the two poles are brought nearer to the circular metal plate, it will apply a magnetic field. A current I is applied to the circular metal plate, and this circular metal plate will rotate about its own axis in this direction, and in this case electrical energy is converted into mechanical energy or kinetic energy. If an electric current I is sent to the circular metal plate, the plate will rotate about its own axis. The AC source sends an electric current I, uh, uh, to the circular metal plate, and in this case the circular metal plate rotates about its own axis. Circular metal plate, in this case circular metal plate rotates. On this circular metal plate no magnetic field acts. That means here no magnetic field acts on this circular metal plate which rotates about its own axis. Now the magnet is brought nearer to the circular magnetic field, circular metal plate. In this case, two poles of the magnet move nearer to the circular metal plate, and electric connection is cut or electric connection is disconnected. No current flows to the circular metal plate. No current flows through the circular metal plate, but the circular metal plate continues to rotate due to kinetic inertia. In this case, disk continues to rotate. Disk continues to rotate due to its kinetic inertia. Kinetic inertia. Due to its kinetic inertia, the disk continues to rotate due to kinetic inertia. And in this case, the two poles of the magnet, this is the magnet and north pole, and we can denote north pole and south pole of the magnet. In this case, north pole and south pole of magnet is brought, north pole and south pole of a magnet is brought near to the circular metal disc, nearer to the circular metal disc, so that this north pole and south pole apply a magnetic field across the axis of the circular metal plate. North pole and south pole of a magnet is brought nearer to the circular metal plate, and these are the north and south pole. North pole and between north pole and south pole a magnetic field B acts. B is the magnetic field which acts across the circular metal plate from north pole to south pole. In this case, an eddy current. In this case, an eddy current flows. An eddy current flows through the circular metal plate in a circular path, and due to generation of electric current I in clockwise direction, a magnetic field B0 will act inwards B0 is the magnetic field which is produced due to generation of circular eddy current in the circular metal plate, and B is the magnetic field which acts from north pole and south pole of the magnet. In this case, B0 opposes B. B0 opposes B. If we switch on, that source will send an electric current to the metal disc, and the disc will rotate about its own axis. If the AC source is disconnected and the magnetic field is applied by bringing the magnet near to the circular disc, in that case the circular disc will be retarded and it will come to rest. Again, we can consider a metal plate, and AC source is placed above the metal plate, and circular magnetic field lines are drawn around the around the coil around the coil of the AC source. These are the circular magnetic field lines around the coil of the AC source, coil which is connected to the AC source. So here we are denoting circular magnetic field lines around the coil which is connected to the AC source. These are the magnetic field lines. Similarly, we can denote circular magnetic field lines on the left hand side of this cylindrical coil which is connected to the AC source. These are the circular magnetic field lines generated from the cylindrical coil which is connected to the AC source, and that AC source will apply variable current to flowing through the cylindrical coil. So these are the magnetic field lines. These are the magnetic field lines. At a certain point on this circular magnetic field line, magnetic field induction due to the alternating current flowing through the circular coil will be acting in vertically upward direction. Vector B is the magnetic field induction vector which is produced due to the variable current coming from AC source through the cylindrical coil. Now we can denote circular currents or eddy currents which are flowing clockwise in the metal plate, and this eddy currents, this is what eddy currents or focal current or circular electric currents, and this eddy currents flow clockwise in the metal plate, and this eddy currents is generated due to variable magnetic field applied by the AC source. Now an opposing magnetic field induction, that is vector B prime. Vector B prime will act vertically downwards, and this opposing magnetic field is produced due to the circular currents or eddy currents. And in this case, the magnetic field due to the alternating current flowing through the circular coil vector B will be opposed by vector B prime. Magnetic field due to AC is opposed by the magnetic field which is generated due to eddy currents. According to Lenz's law, vector B is opposed by vector B prime. So here we are denoting more circular currents or more eddy currents which are flowing clockwise in the metal plate so that this eddy currents produce opposing magnetic field vector B prime which acts vertically downwards to oppose the magnetic field vector B which is produced due to the alternating current. And this is what eddy currents which flow clockwise or circular path which flow in circular path in the metal plate. These are the eddy currents circulate in conductor like swirling eddies in a stream. Swirling eddies in a stream. Eddy currents circulate in the conductor like swirling eddies in a stream. In the diagram, this is the circular magnetic field lines. This is circular magnetic field lines, which is produced due to the variable current flowing through the circular coil connected to the AC source. And here B is the variable magnetic field which is produced due to alternating current, and eddy current flows in clockwise direction. So magnetic field, variable magnetic field B, is opposed by the magnetic field produced by the eddy current. This is the eddy current which flows clockwise, and this eddy current produce a magnetic field in the metal plate. Now eddy current break. Now eddy current break comes into geometries. Eddy current break comes into geometries. Number one, in a linear eddy current break. In a linear eddy current break, the conductive piece is a straight bar or track, is a straight bar or rail, straight rail or bar or track that the magnet moves along. The magnet moves along. In a linear eddy current break, the conductive piece is a straight rail or track that the magnet moves along. In a circular disc, or rotary eddy current break, in a circular disc or rotary eddy current break, the conductor is a flat disc rotor. The conductor is a flat disc rotor that turns between the poles of a magnet. The physical working principle is the same for the both. The physical working is the same for the both. Now we can compare linear eddy current break and circular eddy current break. Left hand side we have the diagram of linear eddy current break, and on the right hand side we have circular disc eddy current break. Circular disc eddy current break. Left hand side, this is a straight bar which is moved with velocity v towards right, and north pole is placed above the straight long bar. And in this case, the magnetic field generated from the north pole will be acting vertically downwards. Magnetic field B, due to this north pole, is acting on the straight bar, and that will be acting vertically downwards. On the right hand side, we have a circular disc which rotates about its own axis or axle. Circular disc which is made of non-ferromagnetic material. And the circular disc rotates about its axis or axle, and north pole and south pole of a magnet is placed. That means the circular disc rotates through the magnetic field produced by the north pole and south pole. Now we can denote the eddy current below the leading edge of the north pole with respect to the straight bar, or for the linear eddy current break. In this case, eddy current flows anti-clockwise just below the leading edge of the north pole, and eddy current also flows clockwise, and here in the diagram you are denoting eddy current which flows anti-clockwise, which flows anti-clockwise with respect to the leading edge of the North Pole, and with respect to trailing edge of the North Pole, eddy current flows clockwise, same as for circular eddy current disk. In this case, eddy current flows clockwise, anti-clockwise and clockwise. Now we can write a linear eddy current. We can draw a diagram of linear eddy current break. Linear eddy current break. A North Pole is placed above the linear metal bar or linear metallic bar. This is, in the diagram, this is a linear or straight bar which is made of non-ferromagnetic substance. This is the straight bar. In this case, the straight bar is made of non-ferromagnetic material or substance. The straight bar is made of non-ferromagnetic substance or material. And this straight bar is moving towards right with a linear velocity v. The straight bar is moving towards right with a velocity v. And the magnetic field due to this North Pole will be acting through the straight bar vertically downwards. The magnetic field due to this North Pole will be acting vertically downwards through the straight bar. These are the directions of magnetic field due to this North Pole. And this magnetic field B, magnetic field induction B, acts vertically downwards through the straight bar. And we can denote eddy currents or circular currents or focal currents. That is, this eddy current will be flowing anti-clockwise. This eddy current will be flowing anti-clockwise, and I is the circular current or focal current or eddy current flowing through the straight bar just below the leading edge of the North Pole. And this eddy current flows anti-clockwise. This eddy current flows counterclockwise, or this eddy current is in counterclockwise direction. That means counterclockwise eddy current flows just below the leading edge of the North Pole. If we consider the magnetic field induction, which is acting from the trailing edge of the North Pole in the straight bar, in that case eddy current generated, eddy current will be flowing clockwise through the straight bar. B is the magnetic field induction which is acting vertically downwards, and eddy current flows clockwise. Eddy current flows clockwise in the straight bar made of non-ferromagnetic substance below the trailing edge of the North Pole. Here I is the eddy current in clockwise direction, which is flowing through the straight bar just below the trailing edge of the North Pole. Eddy current which flows clockwise in through the straight bar just below the trailing edge of the North Pole. In this case, this eddy current which flows clockwise at the trailing edge, and in this case on the left hand side, eddy current in counterclockwise at the leading edge of the North Pole. And we can denote leading edge or leading edge portion and a trailing edge portion of the straight bar. Eddy current in the leading edge with respect to the North Pole flows counterclockwise in the metallic straight bar, and due to flow of eddy currents in counterclockwise direction below the leading edge of the North Pole, a magnetic field B prime will be acting, a magnetic field B prime will be acting which acts upwards. Similarly, the magnetic field B prime will be acting downwards due to which is produced due to eddy current flowing clockwise direction. Here B is the magnetic field induction due to north pole which acts downwards through the straight bar, and B prime is the magnetic field induction. B prime is the magnetic field induction, that is the magnetic flux density due to eddy current flowing in counterclockwise or clockwise in the straight bar. As the magnetic field B due to north pole of the magnet through acting through the straight bar or through the metallic straight bar is increasing as the magnetic field B due to the north pole of the magnet through the metallic straight bar is increasing at the part of the bar under the leading edge of the north pole. Under the leading edge of the north pole of the magnet, here we can denote the leading edge and trailing edge of the north pole which is placed above the straight bar. Leading edge, and in this case the magnetic field B is increasing just below the leading edge of the bar, and in this case eddy current flows counterclockwise. And here the eddy current I is induced. Which flows counterclockwise. Full stop. The induced counterclockwise current under bracket I produces a magnetic field B prime. The induced counterclockwise current flowing through the straight bar just below the leading edge of the north pole of the magnet produces a magnetic field B prime which acts vertically upwards and repels the north pole of the magnet. Now we can denote the trailing edge of the magnet or trailing edge of north pole of the magnet which exists on the right hand side portion of the north pole, and in this case similarly the magnetic field under bracket B acting downwards through the straight bar. Similarly, the magnetic field B acting downwards through the straight bar is the magnetic field B due to the north pole acting downwards through the straight metallic bar is decreasing under the trailing edge of north pole of the magnet. Similarly, the magnetic field B due to north pole acting downwards through the straight bar is decreasing under the trailing edge of the magnet. Hence, a clockwise eddy current under bracket I is induced in the metallic straight bar or sheet under the trailing edge of the north pole of the magnet. Hence, a clockwise eddy current I is induced in the metallic sheet under the trailing edge of north pole of the magnet, north pole of the magnet. In the diagram, the magnetic field acting downwards, the magnetic field B prime acting downwards due to the eddy current flowing clockwise under the trailing edge of the north pole, that is B prime, is the magnetic field which opposes the magnetic field B, which is produced north pole. And here what we can write, according to Lenz's law, according to Lenz's law, according to right hand palm rule or right hand thumb rule, according to right hand palm rule or right hand thumb rule, this clockwise eddy current under bracket I flowing in the straight bar under the trailing edge of the north pole produces a magnetic field B prime, which acts vertically downwards, comma, in the same direction of the decreasing magnetic field, B produced due to the north pole. Hence, the metallic straight bar or the metallic sheet carrying clockwise eddy current attracts the north pole of the magnet. Therefore, both of these forces oppose the relative motion of the metallic sheet with respect to the magnet. Unlike the linear eddy current break, the metal of the disc passes repeatedly through the metallic field, and so disc eddy current breaks get hotter than the linear eddy current break. In the diagram, we have a circular disc of metal or metallic circular disc. This is a circular metallic disc made of non-ferromagnetic substance. Circular metallic disc or sheet made of non-ferromagnetic substance or material. The circular metallic disc rotates about this axle or axis. In this direction, the circular metallic disc rotates, and we can denote this is the north pole of a magnet. And south pole of the magnet is placed below the circular metallic disc. North pole is placed above the circular metallic disc or sheet. Now we can denote the leading edge of the north pole, which is placed above the circular disc. This is what in the diagram leading edge of the north pole is denoted. Now we can denote the trailing edge of the north pole, which exists on the right hand side of the north pole, trailing edge of north pole of the magnet. Due to the leading edge of the north pole, an increasing magnetic field B is acting downwards. B is the increasing magnetic field induction, which is acting on the circular metal disc due to the leading edge of the north pole of the magnet. B is increasing magnetic field due to the north pole of the magnet, and it acts downwards. This increasing magnetic field B acts downwards below the leading edge of the north pole, which is placed above the circular metallic disc. In this case, an eddy current will flow anti-clockwise or counterclockwise due to this increasing magnetic field. This is I. I means the eddy current which will be flowing through the circular metallic disc under the leading edge of the North Pole counterclockwise. So eddy current flows counterclockwise under the leading edge of the North Pole. Leading edge of the North Pole. Similarly, this counterclockwise eddy current will produce a magnetic field B prime in vertically upward direction under the leading edge of the North Pole. And in this case, this leading edge of the North Pole is repelled as the magnetic field B prime due to flow of eddy current in counterclockwise direction. And again, eddy current I will be flowing in clockwise direction in the circular metallic disc just below the trailing edge of the North Pole. I is flowing in clockwise direction below the trailing edge of the North Pole, and in this case trailing edge of the North Pole will be attracted. Hence, both of these forces, repulsive force and attractive force, both of these forces oppose the motion of the metallic disc. Both of these forces oppose the motion of the metallic circular disc. And in this video, obviously this is metallic discs, and these are the North Pole and South Pole. And between this North Pole and South Pole, circular metallic disc or sheet rotates about its own axis. In this case, eddy current flows counterclockwise just below the leading edge of the North Pole. I is the eddy current. This is I, or eddy current, which flows counterclockwise, and here it is also eddy current which flows in clockwise direction through the circular metallic disc below the trailing edge of the North Pole. In this case, an opposing magnetic field B prime will be acting in vertically upward direction due to eddy current flowing in counterclockwise direction in the metallic disc. And this is the direction along which the magnetic field B prime will be acting, and this magnetic field which is acting upwards is due to the eddy current flowing counterclockwise. Similarly, if we consider this portion where eddy current flows in clockwise direction in the circular disc, in this case a magnetic field B prime will be acting in vertically downward direction, which will be in the same direction of decreasing magnetic field B due to the North Pole and South Pole. Hence, both of these forces oppose the motion of the metallic circular disc. In the diagram, this is the axle or axis of a circular metallic disc about which the disc rotates. This is the axis. This is the axis of the circular metallic disc, and now North Pole is brought near this circular metallic disc. This is the circular metallic disc, and which rotates about the axle or axis of the disc, and this metallic disc rotates in anti-clockwise direction, and a south pole is placed below the circular metallic disc and North Pole is placed above the metallic disc, and we can denote this portion. This portion is known as the leading edge of the North Pole, and which exists on the left hand side of the North Pole. This is the leading edge of the North Pole, and on the right hand side the remaining portion is known as the trailing edge of the North Pole, and trailing edge of the North Pole exists on the right hand side. This is the trailing edge of north pole of the magnet. And due to the leading edge of the north pole, increasing magnetic field B will be acting in vertically downward direction. So B is the increasing magnetic field which is acting vertically downward direction due to the leading edge of the north pole. So B is the increasing magnetic field. B is the increasing magnetic field due to the leading edge of the north pole or due to the north pole of the magnet. And in this case, due to this increasing magnetic field, a circular current or focal current or eddy current will be flowing counterclockwise just below the leading edge of the north pole. This is what eddy current. I is the eddy current which flows counterclockwise direction in the circular metallic disc under the leading edge of the north pole. This eddy current flows counterclockwise. Similarly, due to flow of this eddy current in anticlockwise direction, a magnetic field B prime will be acting in vertically upward direction. B prime, here B prime is the magnetic field induction which will be acting in vertically upward direction, that is in the opposite direction of magnetic field induction B due to the leading edge of the north pole. B prime is the magnetic field due to counterclockwise eddy current flowing in the metallic disc. B prime is the magnetic field due to counterclockwise eddy current under the leading edge of the north pole, leading edge of the north pole. So this magnetic field induction B prime due to flow of eddy current in counterclockwise direction, that means B prime, this magnetic field induction B prime acting in vertically upward direction due to eddy current flowing counterclockwise direction. Will oppose the increasing magnetic field B which will be acting vertically downward direction due to the leading edge of the magnet. Both of these magnetic fields, that is B and B prime, both of this magnetic field, that is B and B prime, create repulsive force between the leading edge of the north pole, and the disk. Both of this magnetic field create repulsive force between the leading edge of the north pole and the disk. In this case, here both of this magnetic field B prime and B create repulsive force between the leading edge of the north pole and the disk. And repulsive force opposes the relative motion between the disk and the north pole. This repulsive force opposes the relative motion between the disk and the north pole or leading edge of the north pole. Hence, a braking force will act, or braking force acts due to this repulsive force. Similarly, we can consider the trailing edge of the north pole of the magnet which exists on the right hand side portion of the magnet, and here B prime, not B prime, it should be a magnetic field B2 or B prime which will be acting downwards, and this magnetic field B prime will be decreasing magnetic field which acts downwards due to the trailing edge of the north pole of the magnet. And in this case, an eddy current will flow in clockwise direction through the metallic disc just below the trailing edge of the north pole of the magnet. And this eddy current flows clockwise direction, and this clockwise eddy current will produce a magnetic field B double prime which will be acting vertically downwards in the same direction of magnetic field B, which is actually decreasing due to the trailing edge of the North Pole. In this case, B double prime is parallel to B. That means B double prime and B create attractive force between the trailing edge of the North Pole and the disk, create attractive force between the trailing edge of the North Pole and trailing edge of the North Pole and the disk. And in this case, an attractive force acts between the trailing edge of the North Pole and the disk, and this attractive force attract the leading edge. Attractive force opposes the relative motion between the trailing edge of the North Pole and the circular disk. The braking force of an eddy current. Is directly proportional to the linear velocity. V of the circular metallic disc. Braking force of an eddy current brake is directly proportional to the linear velocity of the metallic circular disc. Directly proportional to the linear velocity of the metallic circular disc. The disc electromagnetic brakes. The disc electromagnetic brakes are used on vehicles such as trains, and power tools such as a circular saws to stop the blade quickly when the power is turned off. A disc eddy current brakes consist of a conductive non-ferromagnetic metallic disc or rotor attracted to the axle of the vehicle's wheel. Disc eddy current brakes consist of a conducting non-ferromagnetic metal disc attracted to the axle of the vehicles with an electromagnet located with its poles on side of the disc, so that the magnetic field passes through the disc. The electromagnet allows the braking force to be varied. When the driver steps on the brake pedal, current is passed through the electromagnet windings. When the driver steps the brake pedal, current is passed through the electromagnet windings, creating a magnetic field. The greater current in the coil, the greater current in the windings, the greater the eddy currents. Greater current the windings, the greater the eddy current and stronger the braking force. Greater the eddy current in the windings, greater will be the eddy currents and stronger will be the braking force. Unlike in the linear eddy current brakes, The metal of the disc passes repeatedly through the magnetic field, so the disc eddy current get hotter than the linear eddy current breaks. Unlike the linear eddy current break, the metal of the disc passes repeatedly through the magnetic field, so disc eddy current breaks get hotter than the linear eddy current breaks.